We have our members are as Becky Nebeker, Landon Brown, Emmanuel Lee, and myself, Randall Scott. So our goal for this project was to create a prototype of a portable device that can take an input image and output that image as braille for those that are blind or severely visually impaired. So how will this work? First, the user will insert their finger into the finger holder, and then they'll take an input text from an image. It'll make a prediction of the text on the image and output that text through the braille display.
So for some of our background, one of the main requirements for our senior project was to create something that would help others, and helping the blind is what inspired Braive. This community is composed of 43 million people worldwide, which is increasing every year. Less than 10% of their youth actually know Braille, and that means that the upcoming generation is going to have a big disadvantage. We found that roughly 26% of the blind community are employed. Upon further research, we found that there was a direct correlation between knowing Braille and employment within this community. And on a more scientific approach, studies have shown that reading Braille has the same impact and benefits as a person with vision has from reading and touching. Hopefully you can see the major need of having affordable, accessible Braille devices, as well as a means to teach Braille, and that's where Braive comes in.
The finger enclosure is used for the user to rest their finger inside so they are able to feel the pins once they are raised. In the first photo, it shows the side view of the finger enclosure. The finger enclosure will accommodate different types of finger sizes. Once the finger is inserted into the housing, the user will feel 6 pinholes on the upper part of the finger, which will be in the correct position. The tactile braille display has a few configurations using 6 pins, springs, pin holders, and platforms. In the first photo, the tactile braille display will house the 6-pin braille formation. The pins will each have a spring to keep the compression on the platform so the pins will not misalign when raised by the gear. The pin holder is an encasing to keep the braille pins from interfering with each other while in motion. In the second photo, the pin is being raised, which will house the finger.
Moving on to the gear shaft. So the gear shaft is probably the most critical component to our design because it performs the actuation mechanism in order to raise the braille pins. The shaft is also interfaced between a servo motor and encoder that trigger that braille output. In this side view here, you can see that the gear shaft is between the servo and the encoder. And on each gear shaft, there are 3 unique gear components that are used specifically to raise each platform on the braille display. In this photo here, this is a bottom view of our design, missing the PCB so we can clearly see the connected gear shafts and the entire braille display.
The outer case will house our inner components and has easy access for the user to access the components. The right side of the outer case has a gray holder which will house the Raspberry Pi. In the next photo, the 2 rectangular cutouts are used for easy wiring from the Raspberry Pi to the PCB. On the left side of the outer case, there are 2 holders. One is for the battery holder that is located to the right of the photo, while the other is for the charging module, which is located to the left of the battery holder. The next few photos will be overall outer case assembled together.
So the assembly design consists of 2 of everything, to be honest. We have 2 servo motors, 2 encoders, 2 encoder fittings, which is where we mount the encoders. We have 2 gear shafts, and we also consist of the design also consists of a PCB mounting point, which is also used to power the devices, and the entire braille display. And this form factor is sort of set up in a stackable design to sort of kind of keep everything in a compact fashion. In this photo here, we can see on this left one, we can see a backplate that sort of can be taken on and off, and it sort of houses the whole inner design of the model. And on this right side here, we have a mounting point for the Raspberry Pi to do a lot of the processing. In this photo here, this is the bottom view of our design. We have a camera module that's used to take in the input image, and then we have two LEDs to sort of kind of give a good lighting for that input image. In this inner design here of the braille display, we can see everything's connected. We have the platform here, as well as the levers that are used to actuate the pins to be raised. And each gear is sort of, at the moment, raising a lever to raise the corresponding pins. And in the final assembly photo here, we can see that the backplate is removed, and we have our inner design within the outer casing, and all our wired connections are made, and there are no wires kind of running out of the box.
Let's talk Tesseract. The OCR in Tesseract stands for Optical Character Recognition. Tesseract is an open source platform owned by Google, and it has a recurrent neural network model that is better for processing data faster. As you see here, we are going to take in an input image of the word senior, and our Tesseract model is going to translate that and make a prediction. As you see, the Tesseract model predicts each letter and passes that data to the Arduino.
Now we're going to talk about the encoder and servo working together with software. You can see in this video the encoder here connected to the servo motor and having the gear shaft in between. And they're ran through by the Arduino, and the Arduino tells it when to go, what direction to go in, and when to stop. Now we'll see the entire project work together as we had designed it. As we mentioned previously, we are inputting the word senior. Due to short time, we won't show the entire word, but you can see the gears moving, and once they both have stopped moving and they go the opposite direction, that means that they're both ready for the next letter to come in. So you see the left gear is ready, and then the right gear is almost ready. We definitely had some challenges with this project. A couple of drawbacks that we had were working with the Raspberry Pi after its update for the operating system with Bullseye. That made it difficult interfacing with the camera module, as well as interfacing with the pin connections for the GPIO pins. We also had a hard time with the accuracy of the encoder. That made it difficult to know exactly when to stop the servo motor and when to and just making it as real time as possible. Our biggest challenge that we faced, though, was actually working with the gear shaft and making that run with its complexity and making it as accurate as possible.
There are a lot of improvements that could be made for future. A lot of physical stuff as well. So first and foremost are the servo motors. We would like to get rid of those and sort of have a better actuating type of component, such as a DC motor. And then we would also like to form factor our physical design a lot more and make it a bit more compact. We could also figure out ways to get rid of a lot of mounting pieces and or at least improve those sections where we need to mount pieces. And then we would also like to create a way for the device to be more alphanumeric and represent a lot of special characters that aren't used at the moment.
Let's open the floor for any questions.